Jai Hind everyone, this is Navjyoti Sharma once again coming in front of you for the subject Fundamentals of Electrical Engineering, which is having a code of BEE 101 under AKTU. We are today going to discuss the solution of the university question paper which has occurred in AKTU 2023-24 in even semester for the same subject. Quickly moving on with the questions. Generally, the pattern is we used to have three sections, section A, section B and C. In section A, we used to have 7 questions which are having 2 marks each, and these are the short questions, small questions having 2 marks. So, the very first question which has occurred in 2023-24 even semester, that is what is unilateral and bilateral element. This is the question from unit 1 which is very regularly being asked, right? So, if we go with the classification of various electrical elements, right, the very important classification is unilateral and bilateral elements, right? So, if at all I go with the classification, what do we mean with this? So, I would prefer it to be in a tabulated one. Say this is unilateral element. What is the property of the unilateral element? That this element, the characteristic behavior of this element it changes when there is a change in the direction of flow of current through that particular element. Likewise, if at all I consider that this is one resistance, right? Having this as the terminal A and this as the terminal B, right? Let the current is entering from terminal A and leaving from terminal B, right? And if this resistance is offering me 10 ohms resistance, fine. Now, if at all I reverse the terminals, right? Likewise, now the current is entering from the terminal B and leaving from terminal A. In this case, will the resistance offered by the same resistor vary? No, right? That means its characteristic behavior, its property is intact even when there is a change in the direction of the flow of current through it. These kinds of elements are being called as bilateral, two surfaces, two sides. That means the element whose characteristic property doesn't change, whose characteristic property does not change. Right? The characteristic property does not change with respect to the direction of flow of current. Those are being called as bilateral elements. So, the best example for these kinds of elements, what we follow, those examples are, if at all I say, is resistor, inductor, capacitor, etc. The basic circuit elements RLC are the bilateral elements, whereas the unilateral elements, so these are the elements whose characteristic property did change, they change with respect to the direction of flow of current flowing through it. These kinds of elements are being called as unilateral elements. Just opposite, here it changes, the characteristic property changes with respect to the change in direction of current. If at all I say, what are the examples? So, here the examples are majorly all the types of semiconductor devices, likewise diode, thyristors, SCRs, transistors, all these, their characteristics behavior changes with respect to the direction of current through them, right? So, these are unilateral and bilateral elements. Now, the second question, that is, what is Kirchhoff's laws? In fact, what are Kirchhoff's laws, right? So, if we say that these are the basic laws being applied to the electrical circuits, these are the basic laws. And what are the laws which we see in the Kirchhoff's law? There is not only one law. We are having 2 laws. One is KVL, that is Kirchhoff's voltage law. And what does this law states? Kirchhoff's voltage law. This law states that, this is once again a very regular question, more or less it is being asked many a times. So, the Kirchhoff's voltage law, it states that in a closed loop or in a closed mesh in an electrical network, the algebraic sum of all the voltages occurring is equals to 0. That is the basic or the smallest statement what can be given. Elaborating this statement, I may be saying in a closed mesh or in a closed loop in an electrical network, the sum of all voltage rise will be equals to sum of all voltage drops in a closed circuit, right? That means if at all I go with this network, right? Say this is R1, this is some R2, this is some R3, this is some R4, R5, this is some V1, right? Now when this is a closed network, in this closed network, the KVL can be applied, Kirchhoff's voltage law can be applied. And what does it states? It states that the algebraic sum of all the voltages in a closed loop is equals to 0. It means what? If we just go through this loop, what are the voltages which will be occurring in this? So here presently we are having, this is the negative polarity and the positive. Considering that the current is flowing in this particular mesh in a clockwise direction, say I1, right? So obviously this is a resistor. Here there will be a voltage drop which will be occurring, and the drop will be occurring in the direction positive, negative, same way positive, negative, positive, negative, positive, negative, positive, negative, right? Now I'm having all the polarities of all the voltages, right? Now I may be writing my KVL equation starting with V1. How can I write it? Now the very first one, if at all I move along with the direction of the current, right? So in this we are moving from negative to positive. That means it is lower potential to higher potential. Whenever we are moving from a lower potential to higher potential, we used to generally consider it as a rise, right? And rise is a positive sign, right? So we'll write it as V1, okay? Next one is the drop will be occurring. What will be the value of the drop which will be occurring across R1? Resistance, the drop which is occurring across a resistance will be given by current multiplied by resistance, V is equals to IR. So the drop which will be occurring in resistance R1 would be given as, what is the current flowing through R1? That is I1, the resistance is R1. And the polarity, if you see, is positive, negative. That means we are coming from a higher potential to a lower potential. It's a drop, higher to lower. If it is a drop, we will be considering it as negative. Here we have moved from negative to positive. It's a rise. So we have considered it as positive. Now it's a drop, plus to minus. So we'll be writing it as I1 R1. Similarly, what is the drop which is occurring across R2? The current which is flowing I1 and the resistance is R2. But this is once again positive to negative. It is a drop. So I'll be writing it as minus I1 into R2. Similarly, minus I1 into R3. Similarly, minus I1 into R4, minus I1 into R5. Anything remaining? No. That is equals to 0. So how many voltages we are having? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 and 6. So the algebraic sum of all the 6 voltages will be equals to 0. So this is Kirchhoff's voltage law. The another law, Kirchhoff's another law, that is Kirchhoff's current law. The another one is Kirchhoff's current law, KCL. And what does this states? Where would this be applied? So the Kirchhoff's current law would be applied not in a closed mesh, but in a closed, but at a particular junction or at a node, right? So the KCL, Kirchhoff's current law, will be applied to a junction. And what is a junction basically? A junction is a point in a network where 3 or more than 3 branches meet, right? That is that point in a network. Node, it is that point in the network where 2 or more than 2 elements meet, right? But the KCL will be applied to the point where 3 or more than 3 branches meet, right? If that is the case, what does this state? It states that at that particular junction in a electrical network, the sum of all incoming current would be equals to sum of all outgoing current, right? So let us assume a junction, right, in a network. Say this is one of the junction in a network which is having various branches being connected. Not only 3, but it is having say 5 branches connected, right? And in one of the branch, the currents in these branches, if at all I say, is say I1, another one is outgoing current I2, another one is incoming I3, I4, and then once again I5. So I'm having 5 branches, 5 currents with various directions, right? Now, if at all I apply the KCL say at junction A, this is say junction A. If at all I apply KCL at junction A, the sum of all incoming current would be equals to sum of all outgoing current. So what are the incoming currents at this particular junction? I1, if at all I see, is the incoming current. I3 is the incoming current. I5 is the incoming current. I2, is it the incoming current? No, it is the outgoing current. Similarly, I4 is also an outgoing current. So the sum of all incoming current becomes I1 plus I3 plus I5. These are all sum of all incoming currents must be equal to sum of all outgoing currents, and the outgoing current is I2 and I4. So the sum of all incoming current must be equal to sum of all outgoing current. Or I may say at a particular junction in an electrical network, the algebraic sum of all the currents must be equals to 0. The same equation I may write it as I1 plus I3 plus I5 minus I2 minus I4 is equals to 0. So the algebraic sum of all the currents must be equals to 0. So these are Kirchhoff's current law. Basically, let it be KVL or KCL, there are certain limitations to these laws, right? What are the limitations to these laws? That these laws will be applicable to linear circuits, right? These laws would be applicable to lower frequency circuits, right? Lower frequency AC circuits, where the frequency is generally the 50 hertz, right? Or the lower frequencies, right? As the frequency gets higher, these laws are not very much applicable, right? They are not applicable to the magnetically coupled high frequency circuits, right? So there are certain limitations with these laws. But basically, all the electrical and electronic circuits are these laws, KVL and KCL laws, can be applied to these electrical and electronic circuits, let that be AC or DC. Now, what is the average power in a pure capacitive circuit, right? In a pure capacitive circuit, what is the average power? Now, we know for any average power, what is the expression for finding the average power? So, if at all I go with, because we know that it's the multiplication, the power is the multiplication of voltage and current, right? And if it is an average, it is a sinusoidal waveform, right? It's a curve. Over a curve, if at all I want to have the average value, then it is going to be 1 upon 2 pi integration 0 to 2 pi p dt, right? Or p d theta, I must say, or omega t, right? So if that is the case, this is where what is p? P is the instantaneous value of the power. Fine. If that is so, 1 upon 2 pi, 0 to 2 pi. What is the instantaneous value of P? Must be equals to the instantaneous value of voltage and the instantaneous value of current. Fine. Once again, what is the instantaneous value of the voltage? Let it be the reference, Vm sin theta. Okay. Then what about I? I know that for a purely capacitive circuit. For a purely capacitive circuit, what is the relationship between voltage and current? If this is the voltage, the current used to lead the voltage by 90 degree, right? The current used to lead the voltage by 90 degrees. So, if V is equals to Vm sin theta, then the current should be equals to Im sine theta plus pi by 2, isn't it? It is leading by 90 degree. So let us apply over here. So this is Im sine theta plus pi by 2 d theta. So this becomes Vm Im sine theta. This becomes cos theta, right? Sine theta cos theta, I may write it as sine 2 theta 0 to 2 pi 1 upon 2 pi d theta, right? Now, if you just see, this is sine 2 theta d theta. That means, once again, the power, the curve for the power, it will be having twice of the frequency, but it will once again be a sinusoidal term. It will once again be a sine term. If that is so, that means over a complete cycle, we know that any sine wave or any cos wave over a complete cycle, its average value is going to be 0. For the first cycle, it will be taking the energy, and for the another cycle, it will be giving back the energy. So the average power and both the circle, the half cycle, for the half cycle, the energy being taken would be once again be delivered back the same amount of energy, right? So it will be cancelled out, right? Similarly, here also for sine 2 theta, once again, if it all mathematically go with the integration of it, substitute the limits, the average value is going to be 0, right? So the average power in a purely capacitive circuit is 0. Similarly, from here itself, many a times this question has been asked, what is the average power consumed in a purely inductive circuit, right? If this is being asked, so the answer, once again, for an inductive circuit, what is the change? Everything is going to remain same. It is 1 upon 2 pi p d theta V into I. But in this case, for an inductive circuit, the current used to lag the voltage, right, by 90 degrees. So instead of plus, it will be minus here. So it will be minus. But once again, sine 2. Once again, it will be having a double of the frequency, but it will once again be a sine wave. Over a complete cycle, its value is going to get 0. So the average power consumed by a purely inductive circuit is also 0. Now, the next question being asked for the 2 marks in section A is, what is the condition for positive voltage regulation in a transformer? Okay, what is voltage regulation? If at all I say, what is the voltage regulation? In a transformer, the voltage regulation is given by the difference between the no load and the full load terminal voltage, right? If at all I say, this is E2 at no load minus the full load terminal voltage expressed as a fraction of no load. And if at all I multiply it with 100, it will give me the percentage voltage regulation, right? And now if at all we are saying that in this case, it is giving me a positive voltage regulation, right? If it is giving me a positive voltage regulation, means that E2 at no load is greater than the terminal voltage V2, which is generally the case. That is in the case if the load is having a lagging power factor or inductive load or inductive load, right? That means for a lagging power factor or for an inductive load, the transformer will give us the positive voltage regulation. Likewise, many a times, another question has been asked that what is the condition for having negative voltage regulation, right? So, the negative voltage regulation will be occurring when obviously the terminal voltage, which is the full load terminal voltage, is greater than the no load voltage, which will be occurring for it will be occurring for a leading power factor load or for an capacitive load, just opposite of it, right? So, the conditions for both the cases are being discussed. For positive voltage regulation, it will be lagging power factor load, and for the negative voltage regulation, it will be a leading power factor load or a capacitive load. Now, the next question being asked is, write the formulae for efficiency of transformer. What is the condition for maximum efficiency of the transformer, right? Okay. So, formulae for efficiency of transformer. What do we understand with the efficiency of a transformer? Say, the efficiency of any device is given by its output power by input power, right? Fine. This power, what we are talking about is the active power. So, output power by the input power. Once again, the output power in terms of transformer, the output power is towards the secondary where the load is being connected. So, it will be given as V2, I2, cos phi 2, where cos phi 2 is the power factor decided by the load. Fine. Input power. The input power is the power taken by the transformer, and that can be obviously related with the output once again, which can be related as output power plus losses. Right? So, once again, I may write it as V2, I2, cos phi 2, which is the output power, plus losses, the losses which are occurring in a transformer. The two basic losses which are occurring in the transformer are the iron loss and the copper loss, out of which the iron loss are the constant losses and the copper losses are variable losses, right? So, the efficiency, if at all I say the percentage efficiency, that is given by V2I2 cos phi 2 by V2I2 cos phi 2 plus Pi plus PCU into 100. That is a very general efficiency term, right? And if you just see here, V2, what is V2? It is the rated terminal voltage. What is I2? The rated secondary current, right? And cos phi 2 is the power factor of the load, right? Pi, iron losses, which is constant for a transformer. PCU, if at all I say this is the full load copper losses, then this becomes the expression for the efficiency at full load, right? This is the efficiency at full load, because all the terms which are there, these are all corresponding to the full load values, right? The same expression I may just write. What is V2I2 if at all I say? What is V2I2? V2I2 is nothing but the VA rating. So, VA rating into cos phi 2, I may just convert this. Once again, the VA rating into cos phi 2 plus Pi plus PCU at full load into 100 will once again be giving me the efficiency at full load, percentage efficiency at full load, right? This is the another way of representing. Similarly, say if at all I say, what will be the expression for the efficiency at half load, right? What is going to happen? Obviously, we know at half load, the current rating is going to be halved, right? The current rating would be halved. It will be by 2. That means the VA rating would be by 2. Power factor, whatever is the power factor at half load. Iron losses, these are going to remain constant. These are not going to change. These are constant. And what is going to happen with the full load copper loss? The full load copper losses would be when the load is halved, the copper losses will vary according to the square of the load. So, if the load is being halved, the copper losses will be by 4 in case if it is half load, right? So, this will be V rating by 2, V rating by 2 and copper losses will be by 4. Similarly, at certain other load, if at all I say, at certain other load, say at any other load which is given by the fraction x, the efficiency of a transformer, say x load, right? So, the expression should be obviously the x time of the VA rating multiplied by the cos phi. Once again, x time the VA rating into cos phi plus the iron losses which are going to remain constant, but the copper losses, they are going to vary according to the square of the load. So, these are the changes. So, I must say this is the final expression for finding the efficiency at any load. Say at x load, that will be given by like this. Now, another question being asked in this is, what is the condition for maximum efficiency of the transformer? right? If this is the expression for the efficiency and we want to have the expression for the condition for the maximum efficiency, then according to the law of maxima, right, just differentiate the efficiency with the function. Efficiency is a function of load. It will vary according to the load. So, just differentiate it with respect to I2 and equate it to 0. Where this is not VA rating, this would be V2I2. I may express VA rating in terms of V2I2. So, just expressing it in terms of V2I2. Right. PCU can also be expressed in terms of I2 as I2 square into R2E. Right. So, just differentiating it with respect to I2 and equating it to 0, the condition for maximum efficiency would be that this X load would be equals to under root of Pi by PCU. Or I must say that the iron losses would be equals to X square the PCU at full load. That means the load at which the iron losses are equal to the copper losses of the transformer, at that load the maximum efficiency will occur. Right? So, we need to write it in a statement that the load at which the iron losses are equal to the copper losses, at that load the max efficiency will occur. The last question in this particular section, that is, a 3-phase 440 volts 50 Hertz induction motor has 5% slip. Okay. So, the slip of this induction motor is 5%, that means 0.05. What will be the frequency of the rotor currents, right? We know that the rotor currents, the frequency of the rotor current will vary according to the slip, right? At standstill, what is the rotor frequency? At standstill, there is no slip. That means the slip is equals to 1, right? No slip, I must mean to say that the slip value is equals to 1. At starting, so at starting, the frequency of the induced EMF or the frequency of the rotor currents is just equal to the supply frequency, which is 50 Hertz generally in India, right? But in running condition, as the motor gains on the speed, as the slip increases, with that the rotor frequency changes and it is given by S times of F. The slip times the supply frequency. Slip is how much? 0.05. The frequency that is being given as 50 Hertz, the supply frequency. So, this becomes 2.5 Hertz. So, this is going to be the frequency of the rotor current with the slip 5%. So, these are the questions in the section A being explained. In the coming lecture, we are going to have the section B and section C as well coming up. Thank you.